short video quickly review the first law of thermodynamics. And then for heat transfer problem, we are dealing with the consequence of heat transfer. So it is either the temperature increase or temperature decrease. So therefore, we need to relate between the heat transfer process with the internal thermal energy of an object. And then this is done by using the first law of thermodynamics. For an object or any enclosed system, the total amount of the internal energy, which we used in the beginning of the semester, we introduced the capital U. It is used in this textbook as a capital U, but here I use the most explicit explanation. So the internal energy, I use the E as ST stands for stored inside the object, and then the total internal energy that is stored in a object. I use this symbol, and then first law of thermodynamics tells us this internal energy change, which I put a delta here, equals to the total amount of the heat that has been transferred into the object or system minus the work that has been done by the system or by the object. So this will be the heat transferred into the system or object, and this work is done by the system. As I pointed out, the Q is transferred into the system, and then the work will be done by the system. So this delta will determine how much has been changed for the internal energy that is stored in the system. And then, of course, if we put with respect to time within a unit time, then everything becomes the rate. So initially, we are talking about the amount. And now if we talk about the rate of the internal energy change, that will be put a dot. That is basically with respect to the unit time, that would equal to Q minus W. Now you also put a dot on each of them. And then here we can use the rate of heat transfer, and then the rate of the work has been done. This is consistent. The lowercase of the symbols is consistent with what we went through last time. And then for the internal energy, E is stored total. It is actually consists of three components. One is the thermal energy or the enthalpy, and then the second one will be the gravitational potential energy, and the last one will be the kinetic energy. And this has been introduced at the beginning of our class using a background video. If you haven't watched it yet, please watch it. Then first component is the enthalpy. And then the enthalpy, the change of the heat or change of the enthalpy will be the enthalpy that flows out of the system, the enthalpy that flows into the system, and then the mass flow rate will be put a dot here to tell you not the total amount of the mass, it's the mass flow rate. And then the second item is the gravitational energy. The g is the acceleration on the Earth, and the z is height. And then for the height, for the exit of the system, and then the height of the inlet of the system multiplied by the mass flow rate. And then the last one is the kinetic energy, the mass flow rate times half of the velocity square at the outlet minus the velocity at the inlet square. And of course, for this type of cases, we are basically talking about a system that is an open system where we have mass flow rate in, mass flow rate out, and usually if the mass doesn't change for the system, the mass actually, the two flow rates are same. But however, the enthalpy of the material that goes into the system versus leaving the system is different. H in and H out, enthalpy at the inlet, enthalpy at the outlet. And then for chemical engineering cases, we are dealing with, water flow rate, air flow rate, and those things. And usually for our chemical engineering cases, the gravitational potential energy and the kinetic energy is negligible compared with the thermal energy, which is the H, or the enthalpy, compared with the enthalpy. And in addition, the work is also typically ignored. So therefore, in this case, as you can see this equation, here. So the W is, the work is ignored, the gravitational energy is ignored, and then kinetic energy is also ignored. So what we are left with is a much simpler equation, that is the heat transfer rate equals to the net change of the enthalpy between the inlet and the outlet. Or if we use the heat capacitance or the specific heat to calculate the enthalpy, then that will allow us to correlate the heat transfer rate Q with respect to the temperature of the flow at the inlet and the outlet. All right.